Good afternoon. It's not a mistake, me taking over the class today. This was arranged. Oh, I'm just checking the numbers. Right. I'll be taking over for today's session. Mr. Selowas is not available for now. So I wanted to find out, I believe at this stage, everyone got a copy of the third, or I've gone through the third video of your chapter 3, which talks to your 3D equilibrium into 3D projection. Right. So that's the one I'm going to run through, just to make sure we are all on the same level. Right. I'm going to share my screen. Just give me a sec. Please make sure you, unless if you have a question, raise your hand. I'll give you the platform. If you are not, please make sure your mic is on, or you mute your mic. Just I don't want to get that feedback. I believe you can all see my screen. Right. I would like to emphasize on something, just to make sure we are all on the same page. So all these slides, what we've gone through and then what's still to come, are being based on the 8th edition, right? The numbering of problems which will be using in the process, as well, are being based on the 8th edition. Let's just make that clear. So obviously one can always compare them to the 9th edition. I believe, I'm not sure if I gave the reason why. If not, the reason was by the time, we were using the 8th edition, right? So all these slides, I did compile them based on the 8th edition. So now when your new platform, your Wiley Plus platform came in this year, so we are kind of forced to use the 9th edition. So it was a bit too late to make that adjustment. That's why most of the time, I think, that's why I'm trying to emphasize on that aspect of everything was based on the 8th edition. Obviously, one can always compare those into the 9th edition. So that was the main reason why we were still using the 8th edition. But I believe from next year, we'll update it to the 9th edition. Right. I guess I've cleared up that confusion, which might be running among yourselves there. So the problem numbering are based on the 8th edition. That's what I'm trying to say. Right. So now back to chapter 3. So far, we've spoken about your 2D. Into your 2D, we had this, should we call the 3 main equations in terms of equilibrium. Sum of force in the x equal to 0, in the y equal to 0, and the moment. So those are the 3 main equations which we've been talking about. So now into 3D, those equations are still applicable, right? The only difference is we need now to bring the aspect on of the z-axis. So that will be sum of x equal to 0, sum of y equal to 0. Now we need to bring the third axis, which is the z-axis. The sum of forces on the z-axis are equal to 0 as well. The same can be said on the moment side. So the moment can be taken around each one of the axes. So into your 2D projection, we were emphasized on the x and y. 3D, we bring the z-axis along. But in terms of the equation, they remain the same. right? So now let's bring the aspect of how do we go about doing some force identification. It boils down to the free body diagram. Right. Let's take the first case where we have a member in contact with a smooth surface or ball supported member. So on the first one, they do emphasize on the nature or the texture of your surface, which is a smooth surface. And on the second diagram, that's why it's your ball supported member there. So now how do we represent that on a free body diagram? We still make use or do the same we've been doing in terms of there will be only one force, your normal force, which will be perpendicular to the surface. Now, in 3D, your normal force in this case will be perpendicular to the floor. And that floor lies with your X and Y, right? So you have your normal force, which would be perpendicular to X and Y, if I should put it in that context. That's how you go about drawing this or the two setups into your on your free body diagram. Now, if you check your second setup, it's where now roughness is being brought up or entertained. So each time when the roughness is being mentioned, roughness bring the aspect of a friction, and the friction must always oppose the motion. Now, if you check on your free body diagram, we will still have your normal force, which should be perpendicular to the floor or X and Y. So now we need to include the frictional force, and that frictional force must always go against the motion. In this case, your member will have a tendency of going that way, and your frictional force should oppose that motion. And furthermore, your frictional force must be parallel to the flow, parallel to X and Y. Right, let's just keep that in mind. Position 3, we have your roller or wheel support with lateral constraint. So we'll take the same approach as we've been doing it with your 2D. Under any roller, you'll have your normal force. That normal force must be perpendicular to the flow, perpendicular to X and Y. So now, because they brought that aspect of lateral constraint, by lateral constraint, we're looking into your y-axis. So it means the movement on the y-axis. So that movement needs to be restricted. That's why they brought your force P there, right? So that is the constraint on the lateral movement of your roller or wheel. Number 4, we have a ball and socket joint. Ball and socket joint. Now, with your ball and socket joint, we need to react into each one of the exercises by making, remember at the support, it's all about trying to react. To react in a sense of to prevent any motion. If any motion takes place, those equilibrium equations are not applicable anymore. We cannot use them. So we need to make sure we have no movement on each one of these exercises. So now with regard to your ball and socket joint, we need to react on each one of the exercises. On the x-axis, you'll have your Rx, Rz on the z-axis, and Ry on the y-axis. Right, that's how we go about representing these reactions each time when you come across your ball and socket joint. Number 5, we have fixed connection or embedded or welded. This is the setup. Now, one can always relate when you talk about fixed connection, embedded or welded. If I take you back in the 2D, where we're talking into your free body diagram exercises, we've mentioned one which was a building, a cantilever beam I don't know if you can still recall what were the reactions or the option to react into that building of your beam, into a concrete or a wall. You could react into X, Y, and apply a moment if need be, right? So the same approach can be applied here. So we'll react in terms of X, Z, and Y, and we can apply moment around each one of those axes if need be to prevent any motion. Remember, it's all about trying to prevent any motion. Right. Number 6, thrust bearing support. That's your bearing in green there, which they've positioned into your X, Z, and Y. So now on your free body diagram, how do we represent this setup? We will still have the reaction on each one of the axes as they've done it, but your moment can be only taken on the Z axis or on the X axis and Z axis. Why? It's because if you check the center line of that shaft, it's parallel to your Y axis, meaning your RY does not have a perpendicular distance. That's why you cannot take a moment around your Y axis, right? But moment can only be taken on the other two axes, X axis and Z axis. Now let's talk about the different setups which one can come across. I think we've done it as well with the 2D. When you talk about concurrent forces at a point, at one point, in terms of diagram, this is what we have. All 5 forces go through one point. So now let's try to project them into your Cartesian system, which is X, Y, and Z. So what are those equations which will sustain your equilibrium condition? It will be these ones. Sum of X equal to 0, sum of Y equal to 0, and sum of forces on the Z axis equal to 0. So it boils down into breaking each one of these forces into the 3 components. Then you add up all the X, all the Y, and all the Z, each one equal to 0. So one need to keep in mind, when you add them up, the direction must be taken into consideration. What do I mean by? If you check, for argument's sake, your F2 is pointing in that direction, meaning all the other components will be pointing into that direction. So if I have to relate that into my Cartesian system, they will be pointing away from the positive direction of each one of these axes. In other words, when I add them up, they should be carrying a minus sign. So when you add them up, one needs to take that into consideration. Where are they pointing at? To the positive side or negative side on each one of these axes when you add them up. So you need to add them up accordingly. All right. Position 2. Now, if those forces are concurrent with a line, which is the setup here. So the 3 equations which will still be applicable, right? In terms of sum of X, sum of Y, and sum of Z, each one equal to 0. So now in terms of moment, the moment can only be taken about Y and Z axis. The reason being because that line where all the 5 forces are being concurrent, it's parallel to the X axis, right? It's parallel to the X axis. It means there is no perpendicular distance for those components on the X axis. They don't have any perpendicular distance. That's why we can't take moment around X axis, but we can on the other 2 axes, Y and Z. That's why you have the 2 moments standing there, right? Position 3, parallel forces. Now one need to find out, are they parallel to which axis? Is it X axis, Y, or Z? In this case, they are parallel to the x-axis. So meaning the equation which will sustain in terms of forces, which will sustain your equilibrium, will be the sum of x equal to 0, right? But moments can be taken on the other two axes, y and z. That's why they brought out those two equations in terms of moment. In position 4, it's just like a summary of what we've spoke about, where you have that set of forces. That set of forces, am I being cut off? Oh, was I being kicked out, or I'm not sure. Can you, I'm just trying to check my connection here. Right. Can you see my screen?
Yes, sir.
Ah, okay. I thought I was kicked out. You never know with ESCOM lately. Well, they are just on top of their games. Anyway, in position 4, that's where, which is like a summary, which summarize all the equations. All right. So now, if I'll do the same as we've done it with your 2D in terms of constraint and statically determinacy, what does it have to do? It has to do with the restriction which we need to put into place. Remember, so far I've been mentioning, let's try to prevent any motion. Let's try to avoid any motion. If a motion takes place, these equations are not applicable anymore. So your notion of constraint and statically determinacy talks to that. So now when you put your constraint, when you put your restriction, don't overdo it or underdo it. You need to do it in a right way. By right way, I mean, can you have your system being statically determinant? Statically determinant means you have a minimum number of restriction, but more effective, preventing any motion into each one of the axes, right? So now let's take the first case where we've got a block and they've put quite a number of restrictions there. Let's now try to test it. If do they really work or not? Let's start into your Z axis. How many restrictions are being put there? There are about 3 of them. Number 4, 3, and 5, which I believe will be sufficient to prevent any motion into the Z axis. Into the Y axis, there are about 2 of them, number 1 and number 6, which I believe can do the job. X-axis, you've got about 1, which is number 2. There is a restriction. I believe it should be good enough to prevent any motion on the X-axis. So now, if you've applied a minimum number of restriction to keep your body into equilibrium, to avoid any motion, now your system will be regarded as statically determinant. In this case, adequate. So the right constraint were put into place. Not too many, but just the right amount, which kept my system into equilibrium, right? Position 2, let's try to test it as well. In terms of Y or Z axis, I've got 2 restrictions. This one here and the one in the corner. Will that be enough? That should be my next question. Because if you check, your block will have a tendency of swerving each side. If you check around that point line there, my block can swerve sidewise, meaning there might be a possibility of a motion, right, on the Z-axis. Let's check on the Y-axis. I've got 2 restrictions, which will be sufficient. X-axis, I have these 2 as well, which would be sufficient, I believe. So the only issue, it's on the Z-axis. I'm not sure. If you check that corner, right, where your 3 axes meet your 0 point, if I should call it that way, it's open, it's unsupported, which might create emotion in the z-axis, which becomes a problem, right? So having such a setup, your system is regarded as partially constrained, meaning there is a possibility of motion, in this case, into your z-axis, right? The next one, z-axis, I've got 3, good. Y-axis, I've got 4, a little bit on top, or kind of overdid it, but they are there. But on the x-axis, there is nothing, no restriction, which becomes a problem. So your system is partially constrained. Number 4, the issue is member 7, or restriction number 7. That's where you kind of overdo it, or you are overdoing it, right? So now it's always good to, it's always advised when you come across a over constrained system. When your system is over constrained, it's regarded as redundant. So now we need to get rid of those extras restrictions, which really don't need to be there, right? In the process, you'll kind of release your system from any additional tension which you are creating by putting those extra restrictions. So in this case, if you come across an over-restricted system, which is classified as redundant, take away those extras, take away those restrictions which really don't need to be there. Turn your system into your statically determinant, which is the position 1, that's the ideal. So in this case, that member number 7, constraint number 7, need to be removed. Then you'll turn your system from being redundant into statically determinate. Right? Do me a favor, if you see someone in the lobby there, can you just accept? Sometimes I don't see who's in the lobby. Whoever can do that, please do it for me on my behalf. Right. Now, I would like you to please just make sure your mic is. All right. So I'd like you to go through the 2 sample problems, which are in your textbook. I think in both editions, by the way. The reason why I'm sending you there just to get a sense of how do we go. It's actually not. Oh, yeah. How do we go 5 and 7? How do we go about applying these equations, your equilibrium equations, into a 3D projection? Right? So please do go through that, just to get a sense of how do we handle this type of problems. So I always try to emphasize on the technique, on the strategy, right? I always believe if you have the right strategy or method, it will be a matter of putting the numbers in to get to the right solution. It's not about the last answer. The focus shouldn't be on the last answer. No, the focus should be on the process, the technique, the strategy. How do we go about doing this? So once you get that right, the rest will fall into place. Right. So start by going through the 2 sample problem. And then you've got these 6 problems, which I would like you to go and look into it. Right. So when you meet Mr. Selowas next time, I don't know when is your next period. So he will talk to these problems. Right. If you have questions, that will be the right platform to engage and raise your issues. And then one can only raise the issues once you have attempted to do them. It's always good to do the problem. That's where you find yourself. Oh, that's where you'll find out If you're getting it, what are you missing? Then you can address it accordingly, right? It's by doing problems, that's how you get it. If doing your problem or doing problems, it's your problem, then you'll have a problem, right? So beside these 6 problems, you have more problems into your tutorials. These 6 were drawn out of those sets of problems into your tutorial, right? So let's not limit ourselves to the 6. It would be nice to go through all 6 and more. Then you'll be comfortable. Remember what I don't know if I can mention to you. My students, I always remind them, all our assessment, which talks to class tests, assignment, exams, we draw our question from the problems which you're supposed to do. So the more problem you do in each module, the more comfortable you'll be, right? So kind of, I do always emphasize, when you set up these assessment, we draw from this problem. So for someone who's kind of taking that effort to go through them, will be at peace, will be comfortable. All right. So now it will be up to you. You know, I think the right approach will be, let me try at least 1 problem a day, minimum 1 a day. That's how I'll discover. If I find it, good. But we do try to shy away, or I'm not promoting the idea of these are the problems which you need to do, and these are the solutions. No, I think there is, if that is what you expect from us, it doesn't work that way. But we are open to assist in terms of, when you come for assistance, you need to start with, I've tried this up to this stage, I don't know how to move from this. Don't come to me or to one of us, oh, I don't know anything. You expect us to do it for you. No, we need to meet halfway, each other halfway. Let's meet each other halfway. That will be the approach to the subject. But if you are or you have that approach of, oh, these are kind of things which are normally talks about, just to make you aware, right? So don't wait in the last minute, because the numbers of problems, they are quite many. So if per day you dedicate 2 problems per day, by the time you realize, oh, I've gone through all of them. And going through all of them, you kind of being exposed to different ways of doing the problem or solving these problems. In the process, you'll be exposed to many strategies on how to go about solving these problems. Then you become comfortable. All right. Do I have any questions from you? I think this will conclude your chapter 3 in terms of theory. Now it boils down to do the problems, right? Do I have any question from you? Is there something which you want me to clarify? I'll stop sharing my screen. Any question from you? Do I have the class rep on the platform?
Yes, sir.
Okay. I've been in discussion with Mr. Selowas in terms of, when is your your first semester test. So I've come up with a date, which will be the 10th of July, which will be a Saturday, from 10 o'clock until 12:30. That test will be done online. the same way you've been doing your assignment. I'll set 5 problems, which will include chapter 2 and chapter 3. Do I have an objection to that? Any objection or any issue?
So can I ask, you said the test will start when and end when?
Oh, I've gave the time. You start at 10 o'clock and end at 12:30. It's a 2-hour paper, but I always give that allowance to avoid, oh, my internet was slow, yara, yara, yara. So I give you a 30-minute extra. Yes, Kekana?
So, are we going to be required to show steps, or like we're just gonna do the steps from the book and then just send answers?
Remember, it will be done the same way you've been doing your assignment. With your assignment, I think you're doing it on the side, and then you just load your answers, right?
Yes, sir. So, sir, are there going to be any attempts or?
Attempt, yes. I'll give you two attempts, and then I will not deduct any marks. Will that be fair enough?
Oh, okay, sir. Yes, sir.
Yeah. Because if you've noticed into your assignment, after the second attempt, I'll remove 15% of the mark allocated to that question. But in this case, 2 attempts straight, no deduction. Just make sure that day you are somewhere where you are connected and, Right. So if I don't have any objection, I'll pull up an official announcement regarding your test on Brightspace, and then you'll take it from there. Right. Do I have any other question? Oh, by the way, I just wanted to extend something to you. I don't know if you are aware of it. I should I say service? Yeah, I lecture industrial student and polymer student. And all my recordings are on the Brightspace under my folder. So those recordings are available to you too. You can go on Brightspace. Under my recordings, you'll have all my recordings. We are all offering the same subject. The content is the same. All the assessments are the same for all: mechanical, mechatronics, industrial, and polymer. The papers are the same. The assessments are all the same. The exams will be the same. So you have kind of all the options being given to you. Right? I don't know if you are aware of that. Maruma, were you aware of that? Oh, is Maruma there? Okay, I see an hand there. Yes, unmute and ask your question.
So will the test be set on only chapter 3 or chapter 3 and chapter 1, chapter 2?
No, I've mentioned that. Chapter 2 and chapter 3. Right. And if you check on Brightspace, I think we gave you, if you go to the planning assessment, the scope of each assessment, I think your first one will be chapter 2 and 3. The second one will be 4 and 5. Right? And I've loaded chapter 4, by the way. I've loaded the videos, part 1 and 2 of chapter 4 on Brightspace. So that will talk to it after your assessment. It's available there. Right. Any other question? Right. If there are no questions, I'm going to call off the session. And have a good one. We'll meet again. Oh, someone just popped in now. Well, anyway. Right. So if there are no questions, let's meet. Oh, your next time, I think you'll meet Mr. Selowas. Well, based on the plan, unless there's something else happen. All right. So have a good one. Bye for now.